Nutrition fuels our bodies and minds. Our strength, mobility, energy, and even mood rely on the right nutrition, and scientists are continually uncovering new secrets. Welcome to Nutrition Unlocked, a podcast celebrating innovations advancing the role of nutrition and health, sponsored by Nestlé Health Science. In each episode, we talk to experts from around the world about the latest topics in health science. We'll bring you insights and discuss innovations that are unlocking healthier futures. Today, we're continuing our healthy aging discussion and looking at chronological age versus biological age. In this episode, we're diving into all elements of biological clocks. What are they? How we can access them and the benefits they can bring to our long-term health. Why do some people feel older or younger than their chronological age? We're joined for this episode by host Rick Jentis.
Thank you for joining me for another episode on healthy aging. In our previous episode, we talked about why we age differently, starting with the mechanisms that happen at the cellular level. In this episode, we're looking at how our chronological and biological ages can be different. We'll also talk about biomarkers of aging and how our immune system can play a role. Joining me today is a very special guest, Bobby Brooke, the co-founder of two longevity research organizations. The first is the Clock Foundation, founded in 2020 with Dr. Steve Horvath, who is a pioneer of epigenetic aging clocks. And second is Intervene Immune, co-founded with Dr. Greg Fahey. This organization focuses on developing treatments for immune system regeneration. Bobby, thank you for joining me today.
Of course. Thanks for having me, Rick.
Well, we all know how old we are because every year we have a birthday. And we turn another year older. So scientists, including you, have found another way to tell how old we are, and that's looking at our biological age instead of our chronological age. So to start, maybe can you explain to us what is our biological age, or what is an epigenetic clock, and how do they work to uncover our body's age?
Yeah, this question about the use of epigenetic clocks to define biological age as a proxy of health status is what's led to the formation of the Clock Foundation. And really our aim is to use these new biomarkers as a proxy of health status and a unique one that can predict future health span and lifespan. Like you pointed out from the beginning, the goal isn't to predict how many birthdays you've had or to predict your kind of exact calendar age. It's really to predict future disease onset and to predict future morbidity and mortality, and also to use it as a tool to assess whether any treatments or interventions you're pursuing are actually working kind of for you. And it's a fairly unique and reliable way to do that that's now becoming available. But maybe for some more background on epigenetic clocks and epigenetic testing, what many people are familiar with is this ability to predict your age. With just a single blood draw, you're able to predict somebody's calendar age to within about 2 years. And you can do that not only for people anymore. There's now technology that's been developed where you can profile age across all mammalian species. So you can use these tools like in preclinical studies. You can also use them, for companion pet testing. So people can test their age and biological age, health status with themselves and also with their companion pets.
That's really interesting. And something you mentioned, which is this idea of measuring health span versus just how old you are. So if I'm 55, but I feel like I'm 35, is that the same thing as having a different biological age versus chronological age?
It is. How you feel is very important. And even a measure of how you feel, some scientists will call it self-rated health. That's like the specific type of survey people will use. That's a pretty good biomarker by itself. People are pretty good with evaluating on their own how healthy they are or not. So if somebody says, I feel 35 and they're actually 55, there's probably something to that. I don't know how many people that are 55 actually feel like they're 35. That's a rare group. They might be, lying to themselves a little bit. Clearly, people are pretty good at evaluating their own health. That said, it's a very subjective biomarker, of course, and epigenetic clocks are a promising molecular biomarker. They're also objective. It's kind of completely, independent to a degree of, how somebody thinks or feels about their own health status. And that's one of its benefits. Of course, there's a lot of things going on within your body every day that you have no ability to kind of detect. I had a friend who just I think it was November, a few months ago, his wife went in for a routine mammogram, pretty healthy, and picked up fairly advanced breast cancer. So, with the aging process is like that, right? There's a lot kind of going on within your body that even if you feel really good, your body is aging. And so these newer molecular biomarkers are pretty good at detecting. They're sensitive to those underlying changes, whereas other metrics just never had, that degree of sensitivity before.
So it's interesting because you talk about how even when you're feeling well, there could be things going on inside that you don't really know what's happening exactly. And we know there are common factors, lifestyle choices that we make that can affect our biological age, things like smoking or not engaging in physical activity. But everyone ages differently, even people who do have the same lifestyle behavior. So I'm curious what your research has taught you about this. Are biomarkers giving you a clue into why people age at different rates, even if they have the similar behaviors? And are the biomarkers like a crystal ball that can tell us what risks we have for certain diseases?
Yeah, for more background on epigenetics, and I guess epigenetic clocks, they're based on DNA methylation. And this is when you are placing different marks across the genome, these epigenetic marks, which epi stands for of above or on top of. So they kind of control your genes. They control your gene expression. And they're a really big part of your cellular state and identity. So they change how your cells and tissues age over time. And they also change how you adapt to your environment, how you adapt to different insults or stressors. And that's related to how people age differently. Some people have been exposed to a rough environment, or maybe they've experienced significant trauma in their lives. But that does get picked up on epigenetic clocks. For instance, grim age is pretty widely considered the most robust mortality predictor. So it predicts overall survival in people, but it also helps predict a variety of different functional outcomes and an onset of different diseases like cardiovascular disease, dementia, and cancer risk as well. But it also picks up, if you had trauma in your life, then you have an accelerated grim age. And that's been shown in veterans with PTSD. It's been shown in people with major depression and with anxiety. So, these kind of stressors, they definitely have an impact and they take their toll on your body. That's one aspect of what can lead people to age a little differently. Beyond that, there are many different camps in kind of gerontology, as I'm sure you're well aware. There are different hallmarks of the aging process, like autophagy or cellular senescence. And so some of these, researchers will kind of debate, is it senescent cells or these kind of zombie cells that are in your body that build up over time and produce inflammation? Is that really what's driving your body to age rapidly? Or is it some other cause? Is it the decline of your immune system that's driving aging? And so there are these different kind of camps. So when you ask, what is it that makes people age differently? It's like a political question a bit. There are these different groups that believe very strongly in one way or another. And there's hypotheses of how aging occurs. And there are groups that believe in programmed aging. They believe that it's kind of evolved and to where aging is proactively driven, by your genes and by gene expression. And then there are other researchers who believe it's all wear and tear. It's like a car. All your parts are kind of wearing out and degrading over time. And that's, more what the aging process is like, and epigenetics are exciting, and it's a biomarker. It's a tool, it's kind of a lens, into these questions. So it can help you tease them apart and help you define an individual path. So in that regard, it's much more than just a number too. When you think about biological age or what's my Grim age score, it's because there is this single metric that kind of tells you how good you're doing kind of relative to the general population. But it is much kind of deeper than that too. And you can pick apart the data and help define your individual path and define how different groups are aging in more similar ways or disparate ways.
So it sounds like there's the classic nature versus nurture discussion of, is it being driven by what my experiences have been or how much of it is predetermined, and maybe it's a little bit of both. So you mentioned that hard living or living in tough environments can have an effect on our biological age. Do you know if there's been any studies in different races or genders to look at how societal factors maybe are impacting people's health status and biological aging?
Yeah, you definitely can detect changes based on socioeconomic status, based off your neighborhood. It gets into what you mentioned earlier about how much is nature versus nurture, but there is just lower income is associated with more accelerated aging. And a lot of that may be going through similar pathways, but it may all be stress related. But certainly when you can detect a signal in disadvantaged communities, I think maybe some of the more exciting work that I've seen is their interventional studies where you're looking at, can I lift this population, whatever their circumstances? Or there are studies they're actually looking at extreme poverty in sub-Saharan Africa, and they have programs in place to lift them up to a better standard of living. And then they're tracking those people before and after with these molecular biomarkers. And the early signs are that you can clearly see an effect. So it's a promising surrogate marker to be using in these studies.
You mentioned this Grim age, which I guess a different type of biological clock. So you have the Horvath clock, which we had started out talking about. What are the different types of clocks out there, and how do they function differently? And it sounds like Grim age gives you an idea of mortality. There's the IAGE clock at Stanford, which maybe talks about inflammation. So maybe can you touch a bit on the different types of clocks and the insights they can give us as we try and manage our health?
Epigenetic clocks as a group, I guess they're based on DNA methylation. One thing that makes them pretty unique is that's a very stable epigenetic mark. And that kind of relates to the power of epigenetic clocks. You have these blood samples that have been banked or stored in freezers for 40 years or 50 years, and where you have a lot of long-term health outcome data with them. And because DNA methylation is so stable, you can analyze these samples and from them predict very long-term health outcomes and overall survival. And that is just one type of measure. I mentioned also there are very simple biomarkers like self-rated health, asking people how do they feel as a survey measure. That's important. That's something that we use in our clinical trials. And I feel like everybody should use that. There are you mentioned the inflammatory clock. Inflammation is a big part of the aging process. It's well known that there's chronic inflammation that increases with age. Researchers will call that inflammaging, and there are measures that can track it. One of the challenges, of that may be the expense. It can be relatively expensive. I think in general, you want to test as many biomarkers as is practical and possible, and you want each treatment that you're testing to have very clear and unequivocal effects, not only on epigenetic clocks, but on a whole host of other biomarkers and also clinical outcomes and on functional outcomes. So you really want to see effects across the board with new treatments.
So getting to a specific cause of aging that's common to all of us are our immune systems and how well our immune systems are functioning and protecting us. We know as we hit 60 that sometimes our immune systems will start to break down as we undergo some dramatic changes that might leave us more susceptible to illness. When you've led research on this, what can you tell us about why this happens? Why are our immune systems deteriorating with age? And is there anything that can be done to slow this process?
Yeah, through our work at Intervene Immune, we've done clinical trials that are focused on immune system regeneration and regeneration of the thymus specifically. And this is a part of your immune system that trains your immune cells, that trains your T cells. The T in, a T cell stands for thymus. And it's basically where your immune cells get educated in early life and they get taught what to attack, what to tolerate. And so it helps create your immune system when you're younger. But when you're older, it degrades or it atrophies with age in everyone. So even by age 40 or so, your thymus is largely replaced by fatty, non-functional tissue. So, that's one major driver of immune system aging. And so people do pretty well, though, like their peripheral immune system will be intact up until maybe your 70s. It's not really until kind of your mid 70s when most people experience a significant immune system collapse. And that's really strongly linked to an increase in morbidity and mortality. But yeah, some of our work through those studies is really aimed towards preventing that immune system, preventing people from falling off this cliff, so to speak, where your immune system collapses.
Finally, Bobby, I want you to put on your far-sighted glasses and tell us what you see happening down the road in 5 or even 10 years from now. Will the research in epigenetic clocks lead to changes for the aging population?
Yeah, I certainly believe they will. These new longevity and preventative medicine trials, they're really ushering in a new wave of treatments, could be far more reliable for addressing the underlying biology of aging. And epigenetic clocks over the next kind of 5 to 10 years, what we expect will happen is that there will be new trials. There'll be ones that kind of reliably show that a reversal of epigenetic aging or epigenetic clocks leads to a long-term improvement of a whole host of clinical and functional outcomes. And really kind of what the practical benefit for people is that there's going to be a lot of really exciting kind of longevity trials that, they can participate in. And we're coordinating a lot of that work through the Clock Foundation. So if people are interested in joining a trial and testing a new treatment, they can reach out to us. We can go directly to our website, www.clockfoundation.org, and find out how they could volunteer, get involved in the study, or simply get testing and get their first epigenetic clock test if they haven't had one already.
Bobby Brooke is the Executive Director for the Clock Foundation and CEO and CTO of Intervene Immune. Thank you so much for listening to part 2 of our 2-part series on healthy aging, chronological age versus biological age. We hope you enjoyed today's discussion and learned something new. If you haven't already, please rate, review, and subscribe to Nutrition Unlocked on Apple Podcasts so you can ensure that you don't miss an episode and you can let others know about the podcast. We look forward to sharing insights and other interesting topics related to the science of nutrition with you soon. See you next time on Nutrition Unlocked.